And welcome everyone. This video, I just want to show a quick overview of the upcoming project. It's probably going to be one of the most expensive projects I've ever undertaken. The reason I want to build a dyno is for tuning my own vehicles and possibly another form of income, renting the dyno out or tuning other people's vehicles. Big reason I need to build one instead of just buying a Hub Dyno, because obviously the easiest thing would be to just go out and purchase a dyno, whether that's a chassis dyno or a Hub Dyno. We'll get into that on the next slide here, but sometimes you can find a chassis dyno used $65,000, $70,000, and a new Hub Dyno. I think the starting price is like 80,000, and that's just not realistic for me. Um, Definitely not currently, and I don't know if that's ever going to be realistic for me. So what is a hub dyno? Well, you may be familiar with a chassis dyno, or as it's sometimes called, a rolling road. This is where you have a drum or a roller. Generally, it's placed in the floor so that it's flush. And some of the drawbacks of this system is you have to strap the car down, and if one of these straps come loose, as this car is accelerating or trying to accelerate, it's creating a force that's pushing the car forward just like as if it was on a road. So these straps are incredibly important, and the angle at which you place them and everything is important. And I have seen these come loose. There's videos on YouTube you can look at, but as the car shifts, the weight transfers, and sometimes they can come loose and the hook fall off, and then with one strap, the car starts walking sideways. It's not always the safest thing. It does work fine. I mean, there's lots of people dynoing cars safely with this system. Another drawback is that because the diameter of the tire changes throughout the run with speed, as well as just kind of how much the tire is squishing down right here, the effective circumference changes quite a bit, and that can really throw off the dyno numbers. At some point, friction also becomes an issue, where if the tire's slipping, you're obviously not reading that, and there's also the frictional losses between the tire and the roller, as well as the whole thing just being very large. I don't really have room to have something like this mounted in my shop, or if I go rent out a building, I'd have to cut the floor, build one of those racks or something that you can drive onto. So it's really not the most ideal thing for me. Now, a hub dyno, this is a professional one. I guess, I'm not sure who builds this, but there's quite a few manufacturers. The hub dyno, actually, you take the wheels off the car and it bolts directly to the hub. There's one on each side, and there's a computer that synchronizes the speed of these. But effectively, it takes all the friction out of the equation. Um, it's directly measuring the torque at the axle. And because it's bolted to it, you don't have to worry about the car going anywhere. I have seen on some really high horsepower cars it's actually able to kind of do a wheelie or start lifting the front end. So at some point you might have to strap the front down, but I really don't plan on um, dynoing a car with that much horsepower. These are also on wheels, so you can, once you unhook them from the vehicle, you can kind of roll them out of the way and store them, or you can kind of take them with you. They're somewhat portable. So you could lift this onto a trailer, sort of flatbed. These are pretty large. So how does a hub dyno work? So I mentioned torque earlier. Torque is the radius or the moment arm times the force acting at that distance, or more specifically, this is actually a cross product. And so if these are vectors, and you take the cross product, then that will be the torque in the shaft. Now, for 90 degrees, then you can just say that it's the force times the lever arm. So how does the hub dyno actually, or any dyno, produce a force? Well, here we see a hub dyno, pretty simple design. We'll get into what's happening here on the inside. And here's where adapters would bolt to that attach to the wheel of the car. Hub dynos typically use air-cooled eddy current brakes to kind of apply a drag to this shaft that the car is trying to spin. Eddy currents are induced electrical currents in a disc that are formed by having either a moving magnetic field or a stationary magnetic field and moving some metallic object through it. And basically what happens is if you have a permanent magnet here, this is, well, it's an electromagnet, but you pass a DC current through here. So you create these stationary magnetic field lines. And as the disc tries to spin through it, that actually generates electricity. But because this disc is conductive, it's a short circuit. And these currents flow locally in this region and produce their own magnetic fields that actually oppose the stationary magnetic field that's set up by the coil. And ultimately what this does is as these magnetic fields fight each other and these currents are produced inside this metal disc, the disc heats up. So you're converting the rotational energy to thermal energy in the disc. And as we'll see, these absorbers are actually have basically giant fans built into these discs to try to dissipate that energy. This is just a really rough, some CAD I threw together. This is an eddy current brake or an absorber, as they're called, or power absorption unit sometimes. Each one of these is just a massive DC electromagnet, and they're actually all wired together in series. Here's the rotors shown here. And there's actually a small air gap in between the rotor and the magnet. The eddy current brake has a bearing internally that connects or supports the shaft within this housing or within the stationary stator, the magnets here. So by placing some pillow block bearings on that shaft and mounting it to a frame, you can actually spin the shaft and these discs while the stator remains stationary. I kind of try to sketch out, as we saw on one of the previous slides, what torque is. So we have the rotation here, and as the stator provides a braking torque to this rotor, the stator will want to rotate with the rotor. But here we'll hold it or pin it with a load cell. So here you can see the perpendicular force vector acting on the lever arm, which is just the distance basically from this location of the pin to the center axis of rotation. If we place a load cell here, we can see with how much force is being placed on that load cell what the torque is about this shaft. And then horsepower can just be calculated by using the simple equation where horsepower is equal to the revolutions per minute multiplied by the torque in foot-pounds. So that's kind of where your distance and your force comes in. You have say 1 foot lever arm and a pound of force, and that would be 1 foot-pound of torque. And that's divided by this constant, which is just a bunch of conversion factors rolled up into one to get between RPM and foot-pounds to horsepower. And speed will be detected using a toothed wheel that produces a square wave, and you can count how much time or what the frequency of these square waves are and get the RPM of the rotor, as you've seen in my other videos. This is kind of a high-level view of what the system will look like. So if we just kind of look at one of these absorbers here, and here's the hub that would connect to the vehicle. There's the one on the right side or the other side of the vehicle. We have the toothed speed sensor here, the load cell, and the stator, the stationary magnetic field, is controlled with a 0 to 192 volt DC signal, or power, I should say. So this will actually be driven by a power supply. All this will be controlled by this controller, which basically will monitor the speed of each absorber with the square wave and looking at the frequency of those. It'll be looking at the force from the load cell, which we can linearize to, say, a 0 to 5 volt signal for the force, and you'll program the lever arm distance into the controller. The controller will output probably a 0 to 5 volt signal to the power supply that will then supply 0 to 192 volts DC to the electromagnets to adjust the braking torque on the vehicle. The controller will be in communication with a desktop or some sort of PC, which will allow you to set either a load that you want the dynos to maintain on the engine, or you could set a speed, so the controller will just try to maintain a set point for the speed. You could also set a ramp rate if you're doing kind of a dyno pull or an acceleration. You'd want to set that acceleration to be constant so that you can work out what the horsepower is, because as you accelerate all this mass, those large rotors, you'll have to take that into account. If you're at a steady state condition, the inertia of the rotors really doesn't matter because you're not accelerating them. Some of the requirements I decided on was I wanted to be able to absorb approximately 1,000 horsepower for around a minute. I mean, it'd be pretty unreasonable to hold any engine at 1,000 horsepower for a minute. I do prefer steady state testing because it really lets you tune in the engine more accurately, so you can adjust the fuel and timing until you reach peak torque. And you don't have the inertial forces that I was talking about earlier affecting your readings. So this was probably a bit of a steep requirement, but it was something I wanted to set going into the project. I wanted to be able to provide up to 1,000 foot-pounds of engine braking torque. Some larger turbocharged engines can definitely produce those kind of numbers. I want it to be able to provide its braking force between 1,500 to 8,000 engine RPM. Some sort of adjustment for the camber, or an adjustable camber setting, and we'll talk about that a little bit later, and be somewhat affordable. I talked about these systems typically cost closer to $80,000, and I'm hoping we can stay under 15,000 for this. Let's look at some examples. This guy, Rainer Flans, I believe this video is called like Dutch Dyno or something. I don't really want to misspeak, but it's always good to look at previous works and kind of get an idea of what other people have done. You can learn a lot from other designs. This one here, you can see the absorber and the rotors. There's those pillow block bearings that it spins about. This one's actually spinning right now. That's why the rotors are blurry. It sits inside this frame, and there's actually a pivot here. And it looks like he's using a bottle jack or some sort of hydraulic jack with maybe some rubber isolator here to be able to tilt the back of this up and down. And that's because cars with independent rear suspension, that camber is going to change as the suspension moves, as well as could be set to different values on different cars. So you need to be able to tilt this mechanism up or down, kind of like that, about this axis here. What he has done is used a small, we'll call this a stub shaft, and two more pillow block bearings to fully support the vehicle. And then this looks like I believe they're called gear teeth shaft couplings, and they allow for some misalignment between the shafts. Not a whole lot, but they do allow for some small amount of misalignment between these shafts. And that way, the only force is acting on the absorber would be the rotational force or the torque. I don't think that's too critical, except it does make sure that you're not applying any kind of bending moment to the shaft or possibly damaging the absorber, though this is a fairly large shaft. Another thing this does benefit from is that if you had a car with a shortened axle, so your flange was back here on a big drag car, something tubbed out with the axle short, this allows you to kind of get underneath the car without this interfering with the quarter or the wheel arches or anything like that. So it keeps the stator away from the vehicle, gives you a little bit more reach on it. This YouTuber, Vic Dyno Hire, made this Hub Dyno. This is actually the first one I've seen when I was initially looking into doing this project. And I gotta say, it's probably one of the nicest ones I've seen. Definitely not putting down anybody else, but I really like the frame design. Looks very clean and simple. He's using airbags to actually, you see it pivots here on this one of these pins here. He's using airbags to actually adjust for the camber. Um, he's also using a stub shaft. It looks like a Fresnelsa absorber. I believe he said this was his power supply. So this would be the control signals coming from the controller, the power supply feeding the power to the rotors, and there's the speed sensor picking up the right there off of this hub, and the load cell that I mentioned earlier. He used looks like a drive shaft coupler. These are typically found on independent rear suspension vehicles, maybe Pontiac GTOs or Holdens and Cadillac Escalade, or not Escalades, but CTS. A lot of BMWs, Mercedes use them as well. I'm not sure if he's relying on that just for any shaft misalignment that may be or may exist between here and the absorber shaft. My only concern with this is that this is meant to handle drive shaft torque, and because of the rear axle ratio, um, there's going to be, approximately 4 times as much torque in the axle, so 2 times the amount of torque per hub of what the drive shaft would see. So I'm not sure what these are rated for. I know people have some pretty high horsepower cars still running these in the drive shaft, but I would start to worry about them. Looks like he's using the plate here that helps hold the kind of the stiffness here, keeps this column that supports the weight of the vehicle from moving with this plate. He's using it to support the wheel speed or the hub speed sensor. From what I can tell, these hubs must be custom, all three of them. And that definitely adds to the cost because these are large pieces of metal, and then you have to bore them out and put a woodruff key or some sort of a straight key slot in them. I think on the other side of the video I saw that this actual stub shaft had splines, which are definitely stronger, but I'm curious to how he got those machined in there because those are extremely expensive. Here you can see all his adapters for different wheel bolt patterns. That is kind of a downside to any hub dynos. You have to have, you can probably get a couple different bolt patterns in each adapter, but ultimately you would need a few. It looks like they have studs in them and attached to his hub on the dyno here. But this is a very nice setup here. Looks very expensive, all this stuff here, but very professional looking. This guy, David Christie, I believe he has some posts on the yourdyno.com forums. I believe he's using a clam branded absorber. I think these are CFK 500s. Again, here's the car adapter, and then the dyno hub, a stub shaft, 2 pillow blocks, and I believe he's also using those gear couplers. I think they're called like gear tooth shaft couplers. Very, very beefy design, very sturdy. A little expensive, but I don't believe these are custom. They may be, but usually you can buy these off the shelf. And these hubs are probably custom. So you can imagine the amount of steel that was machined off of that to be turned into that hub. Very similar design to the last example we looked at. Looks like he has a pivot here, though I'm not, maybe it picks up off of these. I'm not really seeing how it adjusts for camber, though I'm sure it does. There's the load cell, the speed sensor. Here's that support column and another brace holds those pillow blocks. Very nice design as well. This YouTuber, Boost Alf Motorsport, I'm not sure if he speaks English. In his videos, he's not speaking English, but I really like the simplicity of his dyno. I believe these are the clam CFK 500s as well. There's the load cell. He has kind of more of a triangle frame, and he's using a what looks like a trailer jack or something to adjust for the camber. Very simple design, but very effective. I've watched some of his videos. The cars seem very smooth. I don't notice any vibrations. As you can see, he's not using a stub shaft. He just has a hub, this black piece, directly on the keyed shaft of the dyno or of the absorber. And then it looks like an aluminum hub that attaches to the car, which you can make the aluminum piece quite a bit more affordable than the steel, and it would still be plenty strong as long as you had the wall thickness here. So that saves a lot of cost and complexity mounting that directly to the shaft. So the only thing that does is it puts the weight of the vehicle on the shaft, but if you look here, it's probably a 2-inch or 50 plus millimeter diameter shaft. And then you have the other bearing over here, so I doubt you would be bending that. I can certainly do a calculation on the weight of the vehicle, how much, you look at this kind of like a cantilever, you can calculate fairly easily a round shaft, how much deflection there would be in it. What I thought was pretty slick is that he's got this. I had to do some research. I could read this an SKF part number, and this is called like a tapered bushing or taper lock bushing and hub assembly. So this thing's actually split, and it has these threaded slots. They're half, it's like half of a bolt hole, and the other half is in this hub that's also tapered. And when you put bolts in here and tighten it, it squeezes or it clamps on the shaft. So then the torque wouldn't be relying on the key, which I'm not a big fan of transmitting this kind of torque through a single key like that. But if it was clamped on the shaft, then the friction would transmit quite a large portion of that torque. Though I did see in one of his later videos, he replaced this setup with a hub that just was all one piece and it slid on the shaft and used the keyway with a set screw. He said he was having some vibration issues with this, or I guess he wasn't quite able to get it to be trued on the shaft. Not too sure. These aren't terribly expensive, so I may try one because I do like the idea of it clamping to the shaft. So this is a really nice design. There's the speed sensor. And very few parts, very simple, keeps the cost down. Still very effective. Like I said, you don't need any sort of coupler there to reduce torsionals, but having that longer shaft does help you get kind of underneath a car that has a short axle and also keeps the weight kind of from applying any bending moment to the absorber shaft. Here's another one. This is probably about as low cost as you could do this project. This looks like it's probably a Telma absorber out of a truck. That's what these are usually used in, is things like city buses or fire trucks. They're actually used in the drive shaft to try to slow the vehicle down so that you're not using the friction brakes at the wheels and wearing the pads out. But so he probably got this out of an old fire truck or something like that, or an ambulance. And you see very similar design to the last one, more of a square frame. You see he has a jack here with rubber tires to handle the camber, only using 2 pillow block bearings with the hub mounted directly to that shaft. And you just see how, because of that, the rotors and this whole mechanism is closer to the vehicle, but still, you got quite a bit of room there. And I don't know how many, you know, shortened axle or drag cars I'll be dynoing, but something to think about in the design. So that's all of that. Thanks for watching.